Okay, so we're going to start the recording here. What we're doing here, we're going to do chapters 8 and 9, chemical reactions. So I just showed a whole bunch of slides, pictures about chemical reactions, just for an intro. But what we're going to do is we're going to look at the types of chemical reactions here. And so what are the types? It turns out there are three types. Let's say major types, or I'll just say three types that we're going to be considering here. And so let's go ahead and what are those three types of chemical reactions? And so, and this is in no particular order. One type of reaction is the redox reaction. Redox stands for oxidation, reduction. That's one type of reaction. The second type of reaction that we will look at are metathesis reactions. I probably should type this out, metathesis reactions. And the third type of reactions, the acid-base reactions. Then we have subtypes, and so these are the three types of reactions. Now, when you look at your book is going to have like 7 types of different reactions, but some of those types of reactions that they have are subcategories of these. These are the 3 main ones. And so these are the types of reactions we're going to look at. And so let's first focus on redox reactions here. We're going to look at different types of redox reactions next. Here. So we'll go here. I probably should. Redox reactions. And as far as redox reactions go, we have different subcategories of redox reactions that we're going to look at. And so what are the subcategories of redox reactions that we will consider? And these ones would be like element plus element, element plus element, combination / decomposition reactions. Another type would be a single replacement type reaction, single replacement. Another type that we'll see that we're going to use is the chart method. The chart, we're going to be using something called the redox chart, method. This is my name for the method, the chart method. And then we have something called the skeleton, and then etc. More advanced techniques. But these are the ones that these four subcategories of redox reactions are the ones we're going to be focusing on in this class. And so let's take a look at the first one here, the element plus element combination decomposition reaction here. I'm going to look at that here. And so let's look at some examples of this here. When we look at the periodic table, let's try to draw out the periodic table here. Actually, maybe what I'll do is this. Periodic table. Look at the periodic table. We see this. The metals tend to be species that are electron rich, you know, over here. And so you say that these guys here are kind of electron rich, you know. In other words, metals can give up electrons. They have enough. And so let's do that here. Let's see. Electron rich. And electron rich species we call reducers or reducing agents. Reducers or reducing agents. And so something like sodium metals is a great reducer or reducing agent, you know. Even though sodium, you don't think of it as electron rich because sodium has 11 protons, 11 electrons. But it can easily give up that. Well, easily, it doesn't cost too much energy to give up that electron. Something has to take the electron. And so something takes the electron away from sodium. Sodium's left with 10 electrons and 11 protons, giving it a positive charge. Well, what takes the electron? What takes the electron are electron poor species. So over on this end of the periodic table, we'll have electron poor species. And these are oxidizers. Oxidizers or oxidizing agents. And so what might take that electron would be like a chlorine, you know. So if I look at atomic, I'm going to go with atomic chlorine here. And so atomic chlorine will want an electron. You know, well, chlorine, how many electrons does chlorine have? Chlorine has 17 electrons and 17 protons. So chlorine takes that electron from sodium. It's going to end up forming chloride. Chloride's going to have 18 electrons and 17 protons. Chloride. And so even though, yeah, it doesn't seem poor, well, it's poor because it wants 18. It doesn't want 17, it wants 18. And so sodium is rich because it really doesn't want 11, it wants 10 instead. So that's one way of thinking about it. It's a little bit more complex than I'm making it, but I'm oversimplifying it, but essentially that's what's happening. And so what we have here is we have a reaction between sodium and chlorine. When we have this reaction between sodium and chlorine, then what happens is sodium loses electron, chlorine takes that electron, and we end up forming sodium chloride, you know. So this is neutral. Sodium chloride consists of the sodium ions and chloride ions in some lattice structure. And so this is what we have. Now chlorine itself is not so stable. So what we could do is we could take diatomic chlorine or chlorine molecules and break them apart. And break them. So if we take Cl2, break it apart, we can get 2 Cls, you know, for every Cl2. So we'll take a half of Cl2, half a mole of Cl2. And then we can break apart the molecules of a half a mole and get a mole of chlorine. These equations can either be mole ratios, like 1 mole of chlorine, 1 mole of electrons, 1 mole of chloride, or they could be atom or particle ratios. 1 chlorine atom, 1 electron, 1 chloride ion. We can't have half a molecule. So when I have a fraction like this, it has to be moles. Like you could have a half a dozen. Well, we could have a half a dozen of anything. We could have half a mole of anything, but we can't have a half a molecule because a half molecule, well, you can't cut the molecule in half, in other words. And so when we look at the elements, these elements on the left tend to lose electrons, these elements on the right tend to gain. Now the border, of course, the border can extend in here, you know. Whatever element's further to the right is going to take, whatever element is further to the left is going to lose. So nitrogen versus oxygen. Nitrogen versus oxygen, who's going to take the electrons, who's going to lose the electrons in nitrogen versus oxygen? Well, both of these are on the right, so they're both electron poor, but which one's more poor? Well, it turns out the least poor one, actually, we got to get rid of the noble gases. We got to get rid of those, you know, the noble gases, because noble gases are happy as is. And so the least poor species is fluorine, or the most poor species, you know, the least rich species. So oxygen wants electrons more than nitrogen. Whatever is closest to fluorine, fluorine is going to want the electrons the most. In fact, fluorine is the most powerful oxidizer on the table, on the periodic table. And so oxygen takes, nitrogen loses. And so oxygen is the oxidizer. Well, oxygen historically has been a great oxidizer. It takes electrons from lots of things. Oxidizers take electrons. Take electrons. Reducers and reducing agents lose electrons. Lose electrons. And so in this case, even though nitrogen also wants to be an oxidizer, you know, a nitrogen would like to take 3 electrons. If nitrogen gets 3 electrons, then it can form nitride ion, have the same number of electrons as neon. But when we combine them like this, well, there's got to be a winner, there's got to be a loser. We can't have 2 winners, because if we have 2 winners here, then where are the electrons going to come from? And so one's got to be the winner, the other's got to be the loser, and nitrogen is going to be the loser in this case because it's further to the left. And so this loses. So this is the reducer in this case. So it lose. Now, when we take nitrogen and oxygen, how do we predict the products? You know, how to predict the products is not so easy to do. Let's see, can I save this? I know what I need to do. Oh, I guess I'm missing the chat here. Sorry, the chat window was closed. Yeah, you guys are right. I save this, let me think. Okay, I just saved the screen. Okay, so when we do nitrogen and oxygen, one's a winner and one's a loser, but how many electrons can nitrogen lose? That becomes a question. And so this one becomes more complex. And so let's go ahead and predict the product. So I need to clear these. I'm going to try to draw using this instead. Nitrogen and oxygen is air, but nitrogen and oxygen react at high pressure and high temperatures, can react at high T and P. Example, in automobile and diesel engines, especially diesels. Diesels have even higher temperatures and pressures than automobile engines. And so what happens is air gets into the engine and it gets compressed and the temperature goes way up, and the nitrogen and oxygen can actually react, you know. So if nitrogen and oxygen react, nitrogen gas and oxygen gas react, they don't normally react. Under normal conditions, nitrogen and oxygen forms a stable mixture called air. But under conditions of high T and P, we can get it to react. Now, oxygen, how many electrons does oxygen want? How many electrons does oxygen want? Based on its position in the periodic table. Oxygen wants to gain 2. And so, when I think about oxygen, oxygen wants to gain 2 electrons. I'm going to balance everything at the end. So don't worry, I have 2 oxygens here, but I'm not going to balance it yet. I'll balance it at the end. Okay, now how many electrons can nitrogen lose? Well, oxygen's going to take because it's further to the right. And so the thing that's further to the right is going to be the oxidizer. The oxidizer takes electrons. How many electrons does the oxidizer oxygen want? It wants 2 electrons per atom. I have 2 atoms here, but I'll balance it later. And so I have an oxygen that wants 2. Now this is going to be the reducer. The reducer is going to lose electrons. And so how many can nitrogen lose? Well, it can lose +1 all the way to max of plus what? What's the maximum positive charge on nitrogen?
3.
Five. Good, Kazra, you got it. So it's going to go from +1 to +5, the max. And so it depends on the conditions of temperature and pressure, what forms. So for example, if it's +1, if nitrogen's +1, then what's the formula of the product that forms? I need to erase that. Erase this. Nope. Need to customize the buttons. That's a molecular formula. Actually, the molecular formula, N4O2 sounds right for balancing this, but the formula is actually N2O. Do you know what N2O is called? N2O is called dinitrogen monoxide, aka laughing gas or nitrous oxide. And so that's it there. Or nitrogen can be +2. You know, under more extreme conditions, nitrogen loses more electrons. And so under more extreme conditions of temperature and pressure, I might have this form. Well, if nitrogen loses 2 electrons, what's the formula of the compound? Well, it's just NO. NO is called nitrogen monoxide or nitric oxide. If nitrogen loses 3 electrons, then the product might be something like N2O3, you know, maybe. I don't know if this one exists. If nitrogen loses 4 electrons under more extreme conditions, then the product will be NO2. Well, this one exists. This is called nitrogen dioxide. You know. If nitrogen loses 5 electrons, what could form? Well, this would be N2O5, dinitrogen pentoxide. That would be it. So it depends on the conditions. And so when this happens in the automobile engine, these are all toxic to some degree, although nitrous oxide. These are all toxic to some degree. And we get a mixture of them. And so in an automobile engine, the conditions vary a little bit. And so in automobiles, we form NOx, N-O-X, where X, has different amounts of oxygen. So for every nitrogen, we have a different amount of oxygen depending on here. The amount of oxygen increases as we go, and the amount of oxidation increases as we go down, this list. You can see the oxygen ratio increases as we go down. This would have the smallest oxygen ratio here. The oxygen ratio here would be NO1/2. The oxygen ratio here is NO1. Oxygen ratio here is NO1.5. This would be NO2. This would be NO2.5. This would be X for NOx. And so we can see it becomes more and more oxidized as we go down. Do you see that? And so we end up is we get a mixture of NOx. And when you go, if you have an automobile, and one thing you have to do with autos is you have to go for a smog check. When you go for a smog check, they check for the NOx level. You don't want too much NOx because NOx creates photochemical smog. And so these oxides of nitrogen are not good. These are oxides of nitrogen. Oxides of nitrogen. Well, that's complex. But other things aren't as complex. Some things, we don't have this many choices, Nitrogen, we got a lot of choices. But for something like iron, we don't have that many choices, because if I take solid iron and then react it with oxygen, then oxygen is going to want to go 2-. But iron, we only have 2 choices, iron 2+ and iron 3+. These are the common charges of iron. And so we only get 2 potential products for oxides of iron. Iron 2 oxide solid and iron 3 oxide solid here. Both iron 3 oxide is known as rust. Right there. And so we don't have as many choices here. Sometimes we only have 1 choice, and so this is 2 potential products. And it depends on the conditions, how vigorous the oxidizing conditions are. If you got lots of oxygen, it's going to be oxidized to its maximum extent. So you expect iron 3. But as the conditions aren't so vigorous, then maybe iron 2 forms. This is like burning charcoal. If we burn charcoal, we have carbon and oxygen. And carbon's charge varies from +1 to +4. Well, it turns out, +2 and +4 are the most common for this. And so we form carbon monoxide gas or carbon dioxide gas, depending on how vigorous we're burning the charcoal. If you don't have enough oxygen, you're going to form carbon monoxide. Well, that's a problem because carbon monoxide is poisonous, like oxides of nitrogen. CO2 is poisonous, but to a smaller degree. But other things are easy, like magnesium. When we have magnesium solid, there's only 1 choice, and we try to oxidize it with oxygen. The 1 choice is it goes to magnesium 2+ and O2-. And so the product of this is going to be MgO, solid. Same thing with sodium, sodium only goes to plus. Aluminum only goes to 3+. So when we have fixed charges, it's easy to predict the single product. When we have variable charges, we're going to have variable products. And if we have a lot of variable charges, we're going to have a lot of products, potential products. And so the conditions will dictate, which products are formed. Hopefully, when you're burning charcoal, you don't produce much carbon monoxide. Otherwise, you could be in danger, in trouble with that. Okay. And so this is what we do. We predict the products based on the charges that, these things like to form. And so we can look at some examples of that in a bit here. Actually, maybe we'll do some examples. Let's get rid of this. Oops. So this is it. So the element that's further to the right will be the oxidizer. So this is going to be the oxidizer, oxygen, and this is going to be the reducer, hydrogen. Reducers are also called fuels. On the space shuttle, this would be the fuel, and the oxygen would be the oxidizer. Okay, now when we try to predict the products of this, we got to remember that oxygen wants to gain 2 electrons. And then the hydrogen, what's the positive charge? As hydrogen loses, it can only lose 1. And so there's only one product of this, and it's going to be H2O here. And then we balance this. This is not balanced. And so to balance this, it's probably best just to go ahead and double the hydrogens and double the waters. So now we have 4 hydrogens here and 2 oxygens there. And then we add the states. It's gas normally, this is gas normally, and this is liquid normally. So we just added their normal states. So this is called a redox, element plus element redox reaction. Okay, we could do the reverse reaction here. We could take 2 waters and use electrical energy. So this is called electrolysis with that 9-volt battery. And we can just reverse the process. Here we have the 2 waters. The 2 waters are going to go to 2 hydrogens and an oxygen. Yes, here. Now, what's going to help us in understanding these is something called oxidation state or oxidation number. And so let's just do a quick rundown of how to determine oxidation state or number. The first one is elements in elemental form. Elements, the oxidation state, OS, or oxidation number, O, pound or something like that, is equal to 0. Elements. Elements in elemental form, I should say. Okay, now let's look at compounds. And the elements that are further right get their normal charge, basically. And so when we do compounds, actually we do it in this kind of order here. In compounds, we do it like this. Hydrogen is usually +1. And then the group 1 are usually +1, always. That. The same thing with group 2. Group 2 is going to be +2. And then aluminum, scandium, those are +3. Okay. Now, if it's not one of these, then the element that's further right, assign normal charge. Normal would be, what's its charge, what it would like its charge to be. And so further right, did I spell that correctly? Assign, that's supposed to be assign normal charge. All right, so let's take a look at H2O. With H2O, we assign hydrogen first, and so that's +1. And then oxygen is going to be its normal charge at -2 here. The last point here is the sum of the oxidation states is equal to the net charge. And so oxidation states I put in parentheses like this, you know, here and here. And so what we have here is 2 hydrogens. And so we do 2, this is per hydrogen, not per 2 hydrogens. So +1 on each hydrogen. So we have 2 hydrogens at +1, plus 1 oxygen at -2. This should give us a net charge of 0. That's the sum of the oxidation states. So again, that's on each hydrogen here. And so what I typically do is I usually write the oxidation states above the element, but you know, just so I can keep track of them here. And so this will be +1. This is -2. And then this is hydrogen, the element, and elements have an oxidation state of 0. So this is 0, and this is 0. And the same thing, elements, 0. So each hydrogen is 0. 0 plus 0 gives me 0. Each oxygen is 0. Over here, the hydrogen is +1, and the oxygen is -2. Okay, then we can analyze what happened here. When we analyze what happened here, let's take a look at the hydrogen. The hydrogen is going from 0 to +1. And so that means each hydrogen lost 1 electron. To go from 0 to +1, each H lost 1 electron. Come on. Each H lost 1 electron. If we look at oxygen, oxygen went from 0 to -2. So what we can say here is each O gained 2 electrons. Well, we only have, we have 2 O's here. And so that kind of helps us a little bit in understanding these. So here, H went from +1 to 0, so it must have gained. Each hydrogen gained, and oxygen went from -2 to 0, so each oxygen lost 2. And we have 2 oxygens, losing 2 each is 4, and we have 4 hydrogens gaining 1 each is 4. So altogether, all the oxygens lost 4, and all the hydrogens gained 4 in this particular thing. So we're going to be looking at oxidation states. So. Okay, and so your book is, this is also redox. Your book is going to subcategorize these. And so your book calls this a redox combination because we're combining the elements to form a compound. And this is a redox decomposition. Here, like that. All right, let's take a look at some others here. What we can do. Combination reactions. Okay, so the next example we're going to do is we're going to do copper, like copper pennies. Copper pennies can get oxidized. What are the potential products for this? Well, this is an element plus an element combination or redox reaction. So which one's going to take the electrons? Which one's going to lose the electrons in this particular reaction? Yeah, copper will lose actually. Oxygen's further to the right, so oxygen takes. And so what that means is we can assign this. This is, if copper loses, we call that the reducer. And oxygen takes, we call that the oxidizer. historically, oxygen is the most powerful because fluorine is not very common, and fluorine's to the right of oxygen. And so oxygen used to be the most powerful oxidizer. Well, there are more powerful oxidizers now. And so sometimes oxygen can be the reducer. It could lose instead of oxidize. Okay, that means if oxygen takes, then it likes to go O2 minus. But if copper loses, we have a choice. What are the two common charges of copper? Yeah, 1 and 2. So +1 and 2. So if the conditions aren't that severe, it forms Cu2O, solid. This is red-orange, kind of red-orange color. As it becomes more severely oxidized, it forms copper-2 oxide, which is black. And so we could form copper-1 oxide. I don't know if this was on the test, but I hope not. So I expect you to know that. And this one is called copper-2 oxide. Which one is cuprous? Which one's cupric? This one's cuprous oxide, this is cupric oxide. And so when you look at pennies start off with a nice shiny luster, and then pretty soon that luster dulls to a mere red-orange flat color, which is copper-1 oxide. And after a long period of time, those copper pennies turn black because the copper becomes fully oxidized to copper-2 oxide and then stops. And so we see this reaction occur in pennies. First product we form is this, where it becomes gently or slightly oxidized, and then it becomes fully oxidized over time. Now we can revert back. So for example, if I take copper-1 oxide and I heat it up to very high temperatures, then I can revert it back to copper, molten copper, and oxygen gas. Now I have to have a 1/2 here, or I double everything. So I either use fractions or I double. So I get rid of the fraction by multiplying by 2. So I get 2 CuO solid goes to 2 Cu's plus an O2 gas. C is a solid. And so I can either use a fraction if I'm dealing with moles. I could have 1/2 a mole or 1/2 a dozen or whatever. But if I'm dealing with individual particles, I can't have a 1/2 a molecule of O2. And so that's that. Okay, let's take a look at some examples from the book. Let's see. The book will be chapter 8. Antimony, oh, that's forming antimony. Do some more. Oh, here we are. Okay, let's try some of these, except we're going to try to predict the products. So let's see, when lithium combines with oxygen, what should we form? And so let's do that now. This one I have to do using my pen here. Lithium is a solid metal, oxygen is a gas. Oh, forms. So who's going to lose? Who's going to take the electrons here? First off, lithium loses, oxygen takes. So lithium is the reducer. The reducer I'm going to call the Ra. RA stands for reducing agent. And the oxidizer, I'm going to call the OA. OA stands for oxidizing agent. And so oxygen takes, how many does it want to take? It wants to take 2. Now I got 2 oxygens there, but I'm only going to show 1 because I'm going to balance it later. I don't know what the product I'm going to form is. So oxygen, each oxygen wants 2, so I'll just write 1. Oxygen like that. How many electrons can lithium lose? Lithium is fixed charge, so it can only lose 1. And so the product of this particular reaction is going to be Li2O, 2 lithiums for every oxygen. Okay, now I'm going to try to balance this out. When I try to balance this out, I got to just make sure that I have all the atoms present and accounted for. And so I have 2 lithiums here. I only got 2 lithiums, I can make that 2. But over here I have 1 oxygen, I have 2 oxygens here. So that's going to screw things up. And so either I could have 1/2 oxygen or I could double everything. So let's go ahead and just double it now. Here I'm going to have 2 oxygens, but that's going to kick it up to 4 lithiums. So I'll put 4 lithiums here. This is why I don't bother, worrying about these ratios yet. We'll worry about the ratios at the end when we balance it. This is called balancing. Balancing means that, all atoms on the left are accounted for on the right. So we just balance everything out. And so this is it. And do we expect any other products? No, because lithium only has 1 charge, that we can. Now, oxygen is tricky. Oxygen is a bit tricky because oxygen likes to be 2-, but sometimes it's not, Sometimes it doesn't form oxide. Sometimes it could form peroxide, And so some peroxide formation. In the peroxide, oxygen doesn't gain 2 for each. Well, in the peroxide formation, we end up with an O2 2- instead, And so that means each oxygen is a minus. We got 2 oxygens at minus, 2 oxygens at minus. Add those minuses up and add the oxygens up, we get 2 oxygens at 2-. That's it. And these are linked together. They're bonded together. And so if we form peroxide, then it's a different story because here lithium is going to be plus. So if we form peroxide, it's going to be Li2O2. And so it is possible that we form lithium peroxide instead of lithium oxide, based on the reaction. It depends on the conditions that we react it, what we form and certain other things. And so we could have formed lithium peroxide, maybe. And that goes for everything else. But peroxides typically are very unstable and they typically form with, alkali metals like lithium. But here we're forming the oxide, so this isn't going to happen. Okay. This is possible. Yeah, sometimes we form a mixture of products, both form. Nitrogen combines with hydrogen. Now, this might screw you up a little bit, but because of the way it's written. And so nitrogen combines with hydrogen. Okay, who's going to take the electrons? Nitrogen or hydrogen? Who will take the electrons? Okay, look at the periodic table. And which one is further right on the periodic table? Nitrogen. And since nitrogen's further on the right, we're going to say nitrogen takes the electrons. So if nitrogen takes, how many electrons does nitrogen want to take? Well, nitrogen normally has 7 electrons. Yeah, it wants 3 more to have 10 electrons like neon. And so we formed this one, nitride. N3- is called nitride. And then that means hydrogen loses. If hydrogen loses, well, how many can it lose? 1. And so when we combine this, we'll need 3 hydrogens for every nitrogen. So really, we should write it H3N, H3N. But by convention, this is written NH3, H3. It doesn't matter how you write it, H3N, NH3. Usually it's written NH3, but nitrogen took the electrons at -3, and hydrogen lost at +1. And so this is a little bit backwards because usually we put the positive one first and the negative one second. But this is ammonia in this case. It doesn't matter here, you know, it's just, doesn't matter. This says the same thing, hydrogen plus nitrogen. Here. Oh, in here, why is it first? In here, it doesn't matter, you know, which way you write it. You know. Here, there is a little bit of convention, and it's just conventional that nitrogen's written like this. Normally, you would think that if it's NH3 like this, then you normally think of this as being +3, and each of these hydrogens is being minus, because usually the one who is negative is there. And so another name for ammonia is nitrogen trihydride. But it's not really this, it's really the nitrogen has the negative and the hydrogens are positive in this particular case. But nitrogen trihydride is actually one of the actual names for ammonia. Really, it should be written like this, hydrogen nitride, you know, hydrogen nitride rather than nitrogen trihydride. So something like that, trihydrogen nitride. Okay, let's see if we could figure this one out. They're saying diboron trioxide's formed. Would we have predicted that? And so, okay, so let's react boron, which is a solid, plus oxygen, which is a gas. And who's going to take the electrons, boron or oxygen? Who will take the electrons? Oxygen. Oxygen will take. And so oxygen is going to want to go all the way to 2-, you know, then it's happy. Boron, how many will boron lose? Look at the periodic table and tell me how many boron should lose. Boron turns out to be fixed charge in the same family as aluminum. And so boron should lose 3, that's correct. Boron's going to lose 3. And so what's the correct formula for this? Well, I need another oxide. Then I need another boron. And then I need another oxide. And now I have +6 -6, so that works out. And so what we form is diboron trioxide. That's how we can tell what we form. We don't need this. We don't need to be told what's going to form. We could figure it out based on the periodic table here. And so a new diboron trioxide should form based on how many oxygen likes to gain and how many boron will lose. And so B2O3 is a solid, actually, it turns out. So let's take a look what they got here. Oh, we didn't balance it. I forgot to balance it. Balancing it is just making sure. So we got boron solid plus O2 gas. So it's going to yield B2O3 solid. Now we have 2 borons here, so I can multiply it by 2 here. And then I have 3 oxygens here, shoot, and I have 2 oxygens here. So the easiest thing to do is multiply by 3 halves. 3 halves times 2, excuse me, is 3 halves times 2 is 3. And so that works, but fractions, we don't always want fractions. So to get rid of that fraction, we can multiply by 2. So 4 boron solids plus 3 oxygens, gases, is going to yield 2 B2O3 solids. So we could get rid of that fraction there by multiplying by 2. Okay. And So that's what they got here. Okay. What another thing we have is this. Another thing that we have is incomplete combustion. So let's say we're burning something and we're forming a lot of carbon monoxide. Well, what's happening is you aren't completely oxidizing or completely combusting that. And so we have cases like this where, okay, let's take some wood and combust it with oxygen. And let's say we're forming a lot of carbon monoxide gas. We don't want carbon monoxide gas plus etc. We don't want much carbon monoxide gas. That's incomplete. So we got to burn it better. So we could take the carbon monoxide gas and further oxidize it until it forms carbon dioxide gas. And so this would be complete combustion here, you know, or we have plenty. This is not balanced. This is just to illustrate incomplete combustion. This is incomplete combustion. This is more complete. Actually, this will be complete combustion in this case. So when we form something like nitrogen monoxide, it's not complete because when we look at nitrogen monoxide, what are the oxidation states? Here, let's figure out the oxidation states here. Oxygen gets its preferred, you know, which is -2, the further to the right. If oxygen gets its preferred, then nitrogen's the loser. And nitrogen is going to be +2. Good. Those are +2 exactly. And so these are it. So when we look at nitrogen, well, nitrogen's charge, you know, nitrogen's charge varies from -3 to +5. And so we're only at +2. So nitrogen has the potential for losing more electrons. And therefore, if I have nitrogen monoxide, I can attack that further with more oxygen. Just like carbon monoxide. If I have carbon monoxide, I can attack that further with more oxygen to generate carbon dioxide. Well, nitrogen monoxide, I'll do the same thing, attack it with more oxygen. When I attack it with more oxygen, I can form different potential products, you know. So for example, if I attack it with more oxygen, I might form something like a nitrogen dioxide here, you know, or you know, all the way up to dinitrogen pentoxide. If I form dinitrogen pentoxide, then nitrogen's all the way to +5, you know. Here, we're getting close because in nitrogen dioxide, we're at +4. It's still not complete, you know, completely oxidized, but pretty close. And so nitrogen here is going to be +4. And so we went from +2 to +4, but the max is +5. And so if we undergo more vigor in the oxidation condition, we'll go to +5 and form N2O5. But it looks like here they stop at NO2. They stop at NO2, that's okay. So we're not going all the way, but we're going to further oxidize it. This is not an element plus element redox, you know, but this is a redox reaction nonetheless, you know. And so it's comparable to what we've been dealing with already. And so it's a twist on this. And so, yeah, like I said earlier, the more variety we see, the better. And so let's balance this. So we have nitrogen monoxide gas being attacked by oxygen gas, and we're only going to oxidize this to NO2 gas, not all the way to N2O5. And so when we do this here, well, we need to balance it. And I look at this and I see that here I have one nitrogen, I have 3 oxygens here, 2 oxygens here, too many oxygens. So if I take 1/2 this O2, that works, or just double everything other than the oxygen. So if I go 2 NOs, 1 O2 and 2 NO2s, then it's balanced. 2 nitrogens, 2 oxygens plus 2 oxygens, 4 oxygens. 2 times 2 is 4 oxygens, so it's balanced here. And so this would be the further oxidation of NO. We call it oxidation. Oxidation is when the oxidizer attacks. When the oxidizer attacks and takes electrons, we call that oxidation. So further oxidation of NO. We'll go on to the next one here. Aluminum combines with bromine to make aluminum bromide. Okay, this one, there's only one potential product here. You know, we take aluminum solid and bromine. Bromine's Br2. And so here, which one takes, bromine's a liquid, by the way. Which one takes the electron? What would you want the charge of NO to be when the O2 attacks? Well, the charge on the NO is already fixed. The charge on the NO is +2. What would we want it to go to? Well, we want it to go to +3, +4, +5, you know, any of those are okay. And where it goes depends on how vigorously it's attacked, you know. What are the conditions that it's attacked under? So that tells us that. Stop there. Well, who's going to attack? The oxidizer attacks. The oxidizer takes the electrons. So which one's the oxidizer here? Aluminum or bromine? Bromine. Bromine's the oxidizer, attacks and takes the electrons. Well, it's going to attack aluminum. So aluminum, how many electrons does aluminum have to lose? It has 3 electrons to lose. If we have enough bromines, it'll take all of them. And so how many electrons does bromine want? It wants 1. And so we'll need 3 bromines to attack it. 3 bromine atoms. And so what we end up with is AlBr3. You know? And then aluminum's going to end up at +3. So the net reaction here is aluminum solid plus Br2 liquid yields AlBr3 solid. Bromine's kind of interesting because there aren't that many liquid elements, bromine and mercury. Everything else is solid and gas. The 2 liquid elements, bromine and mercury. Most elements are solids. Okay. So doing this, it's not balanced. So one way to balance this is to go 3 halves of bromine. If we do 3 halves of bromine, 3 halves times 2 gives me 3. Or double everything. If we double everything, we get 2 aluminums plus 3 bromines. Yields 2 aluminum bromides. Liquid, solid. And so that's what we have here. Let's take a look. So that's the reaction there. This aluminum, bromine's a powerful oxidizer. You know, pretty powerful oxidizer. Aluminum's a good reducer. You know, a good reducer loses electrons without too much struggle. Bromine's a pretty good oxidizer, takes electrons, even if the aluminum tries to hang on to them. So it's a pretty violent reaction there. Let's see if we can see a video of this particular reaction. Would be kind of interesting. Aluminum and bromine. It looks like a mess to clean up. My audio, like I said, my audio is screwed up. Reaction of aluminum with bromine. So they got, what is that? Aluminum wire or something? This bromine liquid, it's vaporizing. That's bromine vapor. Some chunks of, or that's powdered aluminum maybe. Put in there. Now bromine's going to attack the aluminum. So it starts to attack the aluminum and tries to take the electrons from the aluminum. A lot of heat and light and energy is given off. It's a highly exothermic reaction there. Okay, yes, it's break time. All right, it's break time. We're going to stop here. Just let's let's let this, I'll fast forward this. Okay, this is what aluminum bromide looks like. Now look at that formula. I got to talk about this formula in a minute after the break. So let's stop now. We're going to take a break and then we'll start again. So our break is going to be 15. So let's start again at 3:20. Okay, I'm going to pause the recording here. Okay, one of the things that is a little odd here is normally a metal and a non-metal makes an ionic compound. In this particular case, it's making a molecular compound. Aluminum bromide turns out to be, looks to be molecular rather than ionic. So it's forming molecules that look like this. 2 aluminums, 6 bromides all linked together to form a discrete molecule like that. How would you have known? I wouldn't have known that necessarily. That's just from observation. So why is that, you know, forming this? Although that kind of looks like, this kind of doesn't look like a molecular, it looks more like an ionic salt. But let's take a look at, some of these here. For example, aluminum chloride should form a lattice. And so let's look at AlCl3. That is an ionic lattice. And so let's take a look at the structure. Is this AlCl3? That's weird. AlCl3 lattice. So I'm going to go to AlCl3 structure. Six coordinate layered lattice, yeah. Why doesn't it show these pictures here? Aluminum chloride forms a lattice like this. It just extends in all dimensions, and we have aluminum ions and chloride ions packed together in that lattice. In gas phase, you could vaporize that lattice. Let's see. And so here's this lattice, and it just keeps going on. And so there's different ways of representing crystal structure of aluminum chloride. But in gas phase, it can form dimers. Okay, in liquid and gas phase, it can actually form molecules. So parts of the lattice break off to form molecules like this. And this is an AlCl3 molecule called a monomer. This is at very high temperatures. It's not very stable. The stable form of this is a crystal lattice like this. And so this Al2Cl6 is called a dimer. And those are molecules, but those are unusual, you know, in the gaseous and the liquid phase. Now, what are they doing with aluminum AlBr3 structure? That's not what I want. I want the crystal. Let's go with crystal structure. So that's more specific. So crystal structures are usually determined experimentally. And let's see, monoclinic space group. This also forms a lattice. So I don't know what he's doing with the dimer. This is the dimer here. But let's look at the structure of this. AlF3. AlF3 is the lattice there. And so typically we take, you know, a metal and a non-metal who's going to form an ionic lattice, you know, crystal lattice like this. And so you wouldn't have known. Some do form molecules So for example, PbCl2, do that here. An example would be PbCl2 forms a lattice, like this. This here, that's PbCl2. PbCl4 forms molecules, molecules would be like, what are the molecules? Do we have molecules here? These are things that you just learn from observations, These would be examples of molecules here. AlBr3 would be at like a high temperature. You break apart the lattice and chunks of it break apart, that kind of thing. And so this is kind of interesting what they did for that. Oops. I don't know if the audio was going through for that or not, because my speaker's dead. All right, let's take a look at, what else can we take a look at here? Okay, that's it. All right, when phosphorus P4 combines with chlorine, phosphorus trichloride is formed. Well, let's take a look at that particular reaction and see what we'd have gotten here. Now, when we take phosphorus, P4, and chlorine, Cl2, which one is going to take, which one's going to lose electrons? Who will take, who will lose? Chlorine takes, and so chlorine takes electrons, we're going to Cl minus. Now phosphorus, what phosphorus is in the same family as nitrogen. So phosphorus is either going to want to gain 3 electrons, or it can lose up to a max of 5 electrons. It turns out that when we look at a max of 5 electrons, that means, well, what does that mean? That means +1, +2, +3, +4, +5. Well, that's a lot. That's a lot of different ones. But it turns out not all of these are favored. The 2 favored ones are +3 for phosphorus and +5. And so typically what we see is it'll lose 3 or 5, in that particular family. Let's take a look at what family that is here on the periodic table. Come on. Keep getting thrown for a loop there. Yes, finally I got a decent, except this is in Russian or something. So phosphorus likes to do 3 and 5. Like tin, what does tin like to do? Tin likes to do phosphorus likes to do 3 and 5, but what does tin like to do? Does tin also like 3 and 5, or lead? What does lead like? Two and 4, great. Yeah, tin and lead, those like 2 and 4. Phosphorus, arsenic, antimony, bismuth, all these like 3 and 5. Even, it could potentially go 1, 2, and 4, but the preferred are 3 and 5. Lead, lead could go 1, 2, 3, and 4, but the preferred are 2 and 4. Same thing with tin, and so that's what we see: 2, 4 for these, 3, 5 for these. And so that's something that can clue you in and narrow it down. That's just from observation. And so, for example, here we could form this. If it's 3, here, let me do this. If it's 3, what do we form? So if we go phosphorus with 3, then we need 3 chlorides. So combining these, we're going to form PCl3. So that's one potential product. It's PCl3. PCl3 is called phosphorus trichloride. Or the other potential is if it goes 5, then with chloride, we're going to form PCl5. PCl5 is phosphorus pentachloride. And so these are the two common products. When phosphorus reacts with chlorine, we form phosphorus trichloride and or phosphorus pentachloride here. In this case, they're telling us to form phosphorus trichloride because of the conditions here. Although this looks pretty violent, you know. This is white phosphorus. White phosphorus starts to glow in air. You know, here it's pretty explosive with chlorine. Air has oxygen in it. You know, chlorine's a good oxidizer too, as well. And so let's take a look at, well, let's look at this first here, 3 and 5. So we'll balance this one. So it's white phosphorus, P4 solid, plus chlorine gas, which is Cl2 gas. And this is going to make PCl3, phosphorus trichloride. And so we got 4 here, so I'm going to go 4 PCl3s. And that's going to give me 4 times 3 is 12 chlorines, and so I just need 6 Cl2s. And they'll balance everything out, so this will be balanced. Now PCl3 is a solid. Yeah. So that's what we have. Okay, next let's take a look at some of these other ones here. Those were combination type reactions, you know, or combining things. These are going to be decomposition reactions where we kind of break things apart. So pure hydrogen iodide decomposes into its elements. Decomposition might go to elements. It could go to different compounds, you know, maybe more stable compounds. And so, for example, you know, I told you about the Greeks and calcium carbonate. Here, when the Greeks are heating the calcium carbonate in their kilns, this doesn't decompose into elements per se. It decomposes into a compound, calcium oxide, and an element, CO2, not an element, 2 compounds. So this is an example of decomposition that didn't go into elements. So we have different kinds of decomposition. And this decomposition is very tricky because this is not a redox decomposition. This is a acid-base decomposition. We'll learn how to recognize that later. And so decomposition isn't exclusively, you know, to something like this. So hydrogen iodide, you know, hydrogen iodide is HI. You know, pure hydrogen iodide decomposes spontaneously into its elements. And so if it decomposes into its elements, it's going to decompose into hydrogen and iodine. But it's not balanced, but if we throw 2 in front of there, then it'll be balanced. HI is normally a gas, and H2 is a gas. I2 is normally a solid. That's what we got there. Okay, when sodium nitrate decomposes, so what is sodium? Sodium is Na plus, nitrate's NO3 minus. So sodium nitrate's NaNO3. That's a solid. When pure sodium nitrate decomposes, it decomposes into sodium nitrite. So nitrite's going to have 1 less oxygen, NaNO2, and oxygen gas. So this is a case where the compound decomposes into another compound plus the element here, O2 gas. And so sometimes that happens, you know, compounds don't decompose all the way to the elements, you know, we could decompose into calcium and carbon and oxygen, you know, it didn't go that far. And so here, the sodium nitrate decomposed into sodium nitrite plus O2 here. All right, just 1 second, I have to answer a question. Okay. Here, let me mute this. Just 1 second. No. Oh, was it? Okay, let me check. Maybe I did. I'll look at my computer and see. Okay. I know. That's
no
what.
No one is doing anything.
Okay, I'm back now. Okay, so in this case, sometimes, you take a guess, what's stable and what is not stable. So sodium nitrite, that's a potential product, of something like that. And so we could take certain guesses to see how certain things might decompose, certain compounds could potentially decompose. So one of those compounds could be like this. Well, in this case, this is a redox. So we'll look at some other cases later, acid base and other types of decomposition. Barium peroxide. In this case, barium's fixed charged and it's +2. And so this can't be barium oxide because barium cannot go to +4. So this is a case where we have oxygen not in the -2, it's going to be O2, 2-. And that means barium's +2+. And so each oxygen is -1 here. Breaks down into barium oxide and oxygen. So if we take barium peroxide here, and the reason we know this has to be peroxide is because barium cannot go above 2+. And if this were oxide, it'd go to 4+. So barium peroxide decomposes into barium oxide, which would be that, and oxygen. So this doesn't decompose into elements, this decomposes into a compound plus the element here. This is still an example of redox. It's still an example of redox. Well, let's balance it first. So we've got one barium, 2 oxygens here. We'll need a half an oxygen here. Or we just double everything. So we have 2 barium peroxides, solids. This is going to go to 2 barium oxides, solids, plus O2 gas, like that. And so that's what we have here. Now, how can I tell this is redox? And how can I tell this is not redox? This is not redox here. One way you can differentiate between a redox reaction and a not a redox reaction is by looking at the oxidation states. The oxidation states always change in redox reactions. And so let's compare the 2 oxidation states for the reactions here. Oxygen is an element in elemental form, so its oxidation state is 0. Each oxygen is 0, 2 times 0 is 0. That's it. Now, barium versus oxygen, oxygen takes the electrons, so it's going to be -2 for oxygen, and then barium loses those, so it's going to be +2 here. Now, this one's tricky because barium can't go beyond +2, so +2 max here. This is why we do group 1 first, group 2 first, because we can't go beyond that. Oxygen is going to have to come out at -1 for each oxygen here. And so the barium, nothing happened to the barium. Barium went from +2 to +2, but the oxygen went from -1 to -2, and then -1 to 0. So one of the oxygens here gained, and the other oxygen lost. We got 4 of them, so 2 gained, 2 lost. That's what happened here. And that can happen as well. So this is redox. When we go up here, though, it's different. Calcium is always +2. Oxygen, in this case, is going to be -2. And that leaves carbon. So if calcium is +2, we got 1. And then we got 3 oxygens at -2. 3 times -2 is -6. So -6 plus 2 is -4. So carbon must be +4 here. It's going to be carbon. Calcium is +2. And then oxygen is going to be -2 here. And then here, carbon versus oxygen, oxygen gets assigned first. Oxygen is -2, carbon is going to be +4. So when we look at what happened to calcium, calcium went from +2 to +2. So didn't lose, didn't gain. Carbon went from +4 to +4, didn't lose, didn't gain. Oxygen went from -2 to -2, -2. Oxygen went from -2 to -2, didn't lose or gain. So therefore, we can tell that this is not redox. Redox, there'd have to be winners and losers in the course of the reaction itself. And so here we can figure it out. Sorry, just one more thing I got to take care of. Hello? I think, yeah. All right, I'm back. Sorry about that. Anyway, okay, so recognizing redox and not redox reactions by oxidation state, changes in oxidation state. All right, bromine trifluoride decomposes into its elements. So bromine is kind of tricky because bromine's all the way on the right, you know? When we look at bromine versus fluorine, they're both on the right. They're in the same family. And so, you know, I told you the species further to the right is going to be taking the electrons, but now both of these are all the way on the right here. And so the next thing is the species that's higher up will take the electron, the smaller one. So fluorine's smaller, actually bromine's a lot bigger. And so the smaller one is more effective, the smaller atom. The smaller atom is more effective at taking electrons than bigger atoms are. And so fluorine will take the electrons. So if it's bromine versus fluorine, fluorine takes the electrons. And so this will be the oxidizer. And if that's the case, then bromine has to be the reducer. Well, bromine doesn't want to be the reducer, of course, you know, but it's going to have to be in this particular case because fluorine's stronger. Now, bromine's charge is going to range, the oxidation state is going to range from -7 to +7. +7 is awfully tough, but it could be done, you know. Anyway, let's go on here. And so the higher up species is winner usually. Here, so bromine trifluoride. Well, in this case, bromine trifluoride is BRF3, you know, like this. It's not so stable. It's a gas. So this is going to decompose into elements, bromine and fluorine. And so this is just a balancing. Bromine is a liquid, you know, one of the few liquids on the periodic table. Fluorine's a gas. And so we need to double this. If we got that, we got 2 bromines and then we got 6 fluorines. So we'll need to triple that. That'll work there. This is a redox reaction here. We can tell that this is a redox reaction because elements are 0. And then fluorine takes. So fluorine gets a -1, its preferred charge, and bromine ends up with a +3. So this is redox. Bromine went from +3 to 0. So in this case, it took electrons, and fluorine went from -1 to 0. It lost electrons in the decomposition reaction. Okay, so let's see, 346 now. Start. Okay, let's move on here to back to our PowerPoint. So those are some examples there. element plus element, but a little bit beyond element plus element because we had some compounds in there thrown in there too for decomposition. And the next type of reaction that we're looking at is, okay, so we just did this first one here. The next one we're going to look at is called single replacement redox. Okay, there's a single replacement redox. And so I'm going to type that here. Single replacement reactions. Single replacement reactions follow this kind of pattern here. And let me write down the pattern here. Pattern is, it's going to be A, which is the element. A, you know, this is generic. It could be, you know, Cl2 or whatever, plus Bx, which is a compound, yields Ax plus B. This is one pattern. This is the most common pattern here. Okay, this is a new compound. And B is the element, a new element, I guess you could say, but you know, all these atoms that are here, they're just being rearranged, you know, in terms of what we see. So let's break this down here to an example here. I'm going to take the element magnesium, which is a solid, and react it with HCl, hydrochloric, but this is going to be hydrochloric acid, AQ here. And so we got my element plus compound here. And so using the pattern, what should form here? What's going to form is AX. So A is magnesium, X is chloride, and so it's going to form magnesium chloride. Well, magnesium is 2 plus, chloride's 1 minus. So I form MgCl2, but hey, I don't have enough chlorines. I don't worry about if I have enough or if I have too many until the end. At the end, I'll balance everything by changing the coefficients. Right now, my goal is just to make sure I get the formulas right. Magnesium loses 2, it's fixed charge, and chloride's -1, things like that. And then the element hydrogen, but the element hydrogen, does it like to be atomic hydrogen or does it like to be diatomic molecular hydrogen? It likes to be diatomic molecular, yeah, that's good. And magnesium chloride ends up to be AQ also, and hydrogen ends up to be a gas here. Okay, how can you tell the difference between a redox reaction again? A redox reaction, we can tell by looking at the oxidation states. If the oxidation states change, it's a redox. So what's the oxidation state of magnesium, the element? All elements are 0 in elemental form, so there's no charge. What's the oxidation states here? Well, hydrogen gets +1, and then chlorine gets -1. Then we look over here, who gets assigned first? Chlorine gets assigned first. Chlorine gets -1, magnesium gets +2. See? Or we could do magnesium first too, it's alkaline, or, and then hydrogen's an element, it gets 0. So what we look at here is we look at what happened to magnesium. What happens to magnesium is magnesium goes from 0 to +2. So each magnesium lost 2 electrons. Then what happened to H? H went from +1 to 0. That means H must have gained 1 electron. Each H atom gains 1 electron. This 0 refers to only one of the hydrogens, each, you know, one of them. But both of them have the same charge. And then Cl, well, this -1 refers to 1, and this -1 also refers to only 1 chlorine. And then we have 2 of them, but we'll deal with 2 of them later. But each chlorine, nothing happened, you see. So this is an example of redox. Magnesium lost electrons. What do we call the loser of electrons? The loser of electrons, is that the reducer or the oxidizer? There's the the reducer loses electrons. So this is the reducer. Then who took the electrons? The HCl took electrons. The HCl is the oxidizer. But more specifically, what in HCl took the electrons? Did the chlorine take the electrons, or did the hydrogen take the electrons? Turns out the hydrogen took the electrons. When we look at chloride, nothing happened to chloride. And so what we say is chloride is a spectator, because nothing really happens to the chloride in this case. It's not, it can do other things sometimes, but in this particular case. So what we're going to do is balance this now. And to balance this, we're going to need two HCl's because we have two hydrogens here. And that'll give us two hydrogens here. And then we'll have two chlorines here, and that'll give us two chlorines here. So this would be balanced here. And so that's it. So we can tell that this is redox because the oxidation states change. Magnesium loses, H plus gains. That's the oxidizer. Now, we need a driving force for these. I haven't really talked about driving force for the element plus element, but I'm going to start talking about driving force now. DF. DF stands for driving force for reaction. What we want to do is we want to go from unstable or less stable. Let's say it doesn't have to be unstable. It just has to be less stable to more stable. Less stable in terms of single replacement, we call more active. If it's more active, it's less stable. And so we want to go from more active to less active. And for single replacement, we want to go from a more active A, the element, to a less active element, B. So more active element A to a less active element B. And for that, we need something called the activity series, which ranks the elements in terms of their stability and activity. And so let's take a look at some activity series here. There's activity series in the next chapter. We should take a look at that. The one from the book. Actually, let's look at the one from the book here. This is called the activity series here. And the things at the top of the activity series are, reactive. The things at the bottom are less reactive, more stable. Post this over here. So this is what we're going to be looking at here, the activity series. So for example, gold is very inactive. Gold is stable. Lithium is very active. Lithium is unstable. Lithium, potassium, barium, strontium, calcium, sodium, these are very active and react, sometimes very violently. Gold, platinum, palladium, silver are unreactive. Those don't react. And so what we do is we compare magnesium, the element, with hydrogen, the element. And so when I compare magnesium with hydrogen in the activity series, here, magnesium versus hydrogen, I see magnesium's more active. More active means less stable. And I see hydrogen is less active. Less active means more stable. And so the driving force for this is we're going from more active element to a less active element. The products are more stable. So So this is more active. This is less active. So this is what we call driving force. And so we expect this reaction to occur. Now, if we have the opposite scenario would be going from less active to more active. Then if it's the opposite, then we say that there's no driving force. If there's no driving force, we expect no reaction to occur. So we will be using the activity series here for that. And so what we're going to do is we're just going to get some standard practice with this first, and then we will dig deeper into it next. And so this is a redox reaction again, just like the ones we had talked about previously, except the ones I talked about previously, I didn't talk about the driving force for. We just assumed that there was a driving force for those. So calcium reacts with hydrobromic acid. That's the first one we're looking at here. So calcium is Ca, solid, and hydrobromic acid is HBr, AQ. And so what does this form? Well, first off, we see that this has a pattern, you know, a recognizable pattern. It's A, the element calcium, plus Bx, the compound HBr. What is this going to yield? Well, this should yield AX plus B. And so what is A? A now is going to go from an element here to a cation here. That's a cation. X is going to stay the same, so it's bromide. So we know we have bromide. It's a spectator, so it stays the same. But calcium is going to go to cation. Well, the only cation calcium can go to is 2+. And so if we combine these, we're going to get CaBr2. It's a product of that. And then B, which is H, is going to be converted into the element. Well, that's just H, the element, except H is not stable in atomic form. It's stable in diatomic form. And so we get this. And it turns out calcium bromide is also aqueous. This is calcium bromide here. And so let's balance this. In order to balance this, we'll need 2 HBRs. You know, they'll give us 2 hydrogens and 2 bromines, and then it's all balanced. And then we check for driving force. Well, for driving force, I have to grab the activity series. Okay, it's not on my clipboard anymore. We'll grab the activity series. I guess I probably can't copy it on here. It's not going to work. And so what we're going to do is we're going to compare calcium versus hydrogen. Hydrogen's a gas. Which one is more active? Which one is less active? This is hydrogen gas. So calcium is up here, hydrogen gas is down here. So calcium going to hydrogen is more active to less active. We're going downhill. We want to go downhill. And so calcium going to hydrogen is downhill. It's becoming more stable. So we're good there. And so that would be the driving force. And so let's take a look at their answer here. So they got the same thing, calcium, except they didn't put the driving force here. We did. All right, so I'm going to have you guys try the next one, number 20. Magnesium is placed into sulfuric acid. And so why don't you guys try this one? I'm going to break you guys up into rooms. Let's see, we got 17 people here. We'll do it at We'll do 3 to 4 participants per room. So let's try doing some rooms here. It can be the same group as last time. Okay, tell me. All right. Let me arrange that then. I'm going to create the rooms. Me. Okay. Okay. Let me know if you have a preference. If you don't have a preference, then I'm just going to assign them randomly. Okay. And if you want, I could reassign. One room is going to have 5 people. So let's try these out and see if you guys can figure what we got here. Okay, so go ahead and join the rooms and let me know if you want to switch around. I can switch you guys around as well. The driving force for this, again, is just going downhill. We want to go downhill, so we want to start up high and then we want to go down low. This is the driving force. So we're going to do this one, magnesium and sulfuric acid. Okay. Magnesium and sulfuric acid. Give that a shot. See what you get. Okay. I'll check in with you guys in a bit. That's the first one, magnesium and sulfuric acid. Then we're going to continue here as well. Magnesium and sulfuric acid. 21's chlorine gas is bubbled through aqueous solution potassium iodide. That's the next one. And the next one is copper metal combines with aqueous silver nitrate. So give these 3 a try and see how you get. I'll check in with you guys in a minute. Let me pause it, the recording here. Okay, we're going to start again here. And so what did you guys get for the first one, number 20? Well, number 20 is going to be magnesium. Magnesium, is it solid, liquid, or gas? It's a solid. Good. What did you get for the formula for sulfuric acid? Sulfuric acid is sulfate. So all we have to do is figure out what sulfate is. Sulfate is SO4 2 minus. 2 minus. And so therefore we're going to need 2 hydrogens. Having 2 hydrogens, this is called a diprotic acid. And so H2SO4 is a diprotic acid here. What did you guys get for the state of this, H2SO4? Solid, liquid, gas, or aqueous? Solid, yeah, we could, well, that's one of the things that comes up, you know, what is the state? You know, and it turns out the state of H2SO4 is aqueous. It's soluble in water. Liquid is if it were pure, but in this case, sulfuric acid is a mixture of the H2SO4 with water. Okay, and so what did you get as your products for this here? Yeah, good. That's correct. That's the right. MgSO4 plus H2. So both of you guys have that right. Now, for MgSO4, what did you get as the state here? Solid, liquid, gas, or aqueous? It turns out aqueous is correct for this, but sulfates are very tricky. H2, what did you get for the state for this one? H2 is a gas, we know that. All right, it turns out this is already balanced, so we don't have to change any of the coefficients. The coefficients are the number in front, they're all 1. And so it's 1 to 1 to 1 to 1 mole ratios. It's all balanced. The only thing that's missing is the driving force. And so did you guys get the driving force for this? And so we want to take a look at the activity series. And when we look at the activity series, at the top of the activity series, this will be the activity series, is lithium. Lithium is the most active. And at the bottom of the activity series is gold. Actually, platinum's even lower. You know, platinum's down here. But these are the least active. And so hydrogen's somewhere in kind of in the middle. So hydrogen's here. H2 gas. These are all metals. Solid, solid, solid. And so where's magnesium? Magnesium turns out it's up here, around here. The alkali metals and the alkaline earth metals are the most active. Those are the metals that are furthest to the left. And those are good reducers. Those lose electrons fairly easily. And so magnesium is an alkaline earth metal. Lithium is an alkali metal. And so alkali metals are a little better. But here we're going downhill. So we're starting off at magnesium and we end up going downhill to hydrogen. So we start out at magnesium and go downhill to hydrogen. That is, we're going from something that's less stable to something that's more stable. And so the activity series goes like this. We say this is more active. And then this would be less active. Is that what you guys got? Did anybody get something different than that? Or did you not? I suppose some people didn't do the activity series because I didn't put it up. It's in your book though. But that would be the last step. We need to know what the driving force is. And so this is a driving force. Now, if we were going uphill, then that's not favorable. And so if we're going downhill, we say that's a driving force. If we're going uphill, we say that's a no reaction. NR stands for no reaction because it's not going to go uphill. It's only going to go downhill, what we call spontaneously or naturally. Okay, now to better analyze this, we need some material from chapter 9. And so to better analyze this, and all reactions, to better analyze reactions, especially reactions involving water, better analyze what we call aqueous reactions. We need to look at two things. We need to look at solubility and electrolyte properties. So if something's soluble, then it forms aqueous, you know, aqueous. So if soluble, the state should be aqueous. So it turns out sulfuric acid is soluble in water, and therefore it's aqueous. Magnesium sulfate is soluble in water, therefore it's aqueous. Hydrogen gas is not soluble in water. And solid magnesium metal, you can't dissolve magnesium metal in just plain water. It doesn't work. You can eat away magnesium using acid, like what we're doing here. We're eating up the acid. This is a redox reaction. We're eating up the acid with the, eating up the metal with the acid here. And so this is successful, but we lose the metal, it turns into salt here. Okay, and then the hydrogen gas just bubbles out of the water. And so we have different solubilities, like metals are insoluble, you know. And so these are rules, you know, and rules aren't always perfect. Sometimes we have to look up the solubilities of themselves. But there are two definitions for solubility. The first definition for solubility is, does it dissolve or not? This is qualitative. So salt, is salt soluble? Yeah, salt dissolves in water. Is sugar soluble? Yes, sugar is soluble, it dissolves in water. Is glass soluble? No, glass is not soluble. If it's not soluble, we call it insoluble. And so we give different codes for this. Does it dissolve? If it dissolves, then we call it soluble. And we give it an an AQ, sorry. Or if it's soluble, sometimes we call it S, but this S means soluble. It doesn't mean solid. Okay. It might be slightly soluble, that is, it's borderline soluble. And so if it's slightly soluble, sometimes we'll call it SS, slightly soluble. And if it's slightly soluble, it might be just solid, liquid, or gas, you know, it just doesn't dissolve. Solid, liquid, or gas, but not aqueous. If it's insoluble, then it just doesn't dissolve, and we call it I for insoluble, and therefore it's going to be solid, liquid, or gas. You know, here a tiny bit dissolves, but not enough to really change things. So these are the states that we expect. And so we need some solubility rules to do this. So we use, for qualitative, we use solubility rules. There are two sets of solubility rules that we use. One for molecular compounds. For molecular compounds, we use the solubility rule that's called like dissolves like. So, for example, oil and water are unlike, and so oil and water don't mix at all. But certain things are water-like ethanol, you know, alcohol. It depends on what alcohol. Most alcohols that you deal with like water, you know, because alcohol and water are similar, whereas oil and water are dissimilar. You know, oil likes oil, and so we could dissolve different oils together, but alcohol and water like each other as well. But if you try to dissolve oil and alcohol, it might not be successful. And the same thing, vice versa. So like dissolves like. And then we have the solubility rules for what we call ionic compounds. Ionic compounds are just compounds that consist of ions, you know, so ionic compounds. For ionic compounds, the solubility rules are a bit more involved, and normally you're supposed to memorize these solubility rules, and it can become a lot of work to memorize these, but it pays off in the end to memorize some solubility rules. So let's take a look at some solubility rules here. There are going to be just 7. These are simplified. There are more complex solubility rules in, let's say, your book, but we aren't going to look at it. And so the first thing we look at is the cation. If it's a group 1 or ammonium, group 1 and ammonium cation salts are all soluble. And it doesn't matter what the anion is. Anion could be whatever. And so here, group 1 in ammonium could be like ammonium carbonate, ammonium phosphate, or it could be sodium carbonate, sodium phosphate. These are all soluble. Okay. If it's not one of these cations, we go to the anion next. And so we'll take a look at some different anions. The anions that we're going to consider, the first set are nitrates, chlorates, and acetates. So nitrate, we look at the periodic table, it's NO3 minus. Chlorates are ClO3 minus. These are all 3 oxygens. And acetates, well, acetates we've got to just memorize 232 minus C2H3O2 minus. Nitrates, chlorates, and acetates are all soluble. So it doesn't matter what the cation is. We could do lead, let's say lead-2 acetate. Lead-2 acetate should be soluble. Or chromium-3 nitrate. Chromium-3 nitrate should be soluble. It doesn't matter what the cation is, as long as it's one of these 3 anions, they're all soluble. Okay, the next anion that we consider are chlorides, bromides, and iodides. Chlorides, bromides, and iodides are all soluble except three cations, except when combined with silver ion. So silver chloride, silver bromide, and silver iodide are insoluble, and those form a solid salt, like this, an S, solid salt. Lead-2 chloride, lead-2 bromide, lead-2 iodide, insoluble, and so those form solids. Lead-4, however, many of those are soluble, so lead-2 and lead-4 behave differently. And mercury-1 is that diatomic, cation, Hg2 So mercury-1 chloride, mercury-1 bromide, and mercury-1 iodide are insoluble. They get this I designation and they stay solid, because these salts, most salts are solid. Very few are liquids. None are gases under normal conditions. Okay, after we look at chlorides, bromides, and iodides, we look at the next anion. And the next anion would be sulfates. Sulfates are soluble except for which ones? Now, there's going to be more exceptions for this, and so let's try. I'm going to try to write them all down. Silver, I'm going to put a little asterisk here because silver is slightly soluble. It's borderline, and so it's not really insoluble. It's SS. So it might dissolve, it might not dissolve. Silver, and then we have lead too. So lead-2 sulfate is insoluble. That's going to be a solid. Mercury-1 sulfate is insoluble. That's also going to be a solid. But now we're going to have mercury-2. So mercury-2 sulfate is also insoluble, forms a solid. And we're going to have calcium. Calcium sulfate turns out to be insoluble, I, and it's going to remain as a solid, S. Calcium, strontium, and barium. Strontium sulfate is insoluble. It's calcium, strontium, barium, yeah. And barium sulfate is insoluble. However, magnesium sulfate turns out to be soluble. So magnesium sulfate is one of the one of the rules here. One of the rules is that sulfates are soluble. However, if it was calcium sulfate, forget it. Calcium sulfate should have an S here, not an AQ, because it's insoluble, so it remains a solid. Whereas magnesium sulfate's a solid salt that dissolves in water, so it gets the AQ here. And so here we could have told that. Here, this acid's a group 1. Hydrogen's in group 1. And so we assume that all group 1 compounds are soluble, and so this would be soluble, as long as it's ionic, and so acids are ionic. Fairly ionic, so that's why this is AQ. Magnesium is just a metal. Metals aren't soluble, and H2 is a gas. H2 is what we call non-polar gas, so it doesn't like water. There are some gases that love water, like HCl gas loves water. Okay, so B, C, and D are anions that are mostly soluble. Then we're going to go to anions that are mostly insoluble next. And so what are the anions that are mostly insoluble? So let's take a look at some of these here. I'm going to erase some of this stuff here. Okay, I guess that doesn't work here. Can't erase this. All right. I'm going to save this, and then let's save this, and then I'm going to make a new whiteboard. All right, I'm going to have to clear all drawings maybe. I can't seem to erase specific ones. All right, so A, B, C, D, E comes next. So let's write that up here. When I look at this next one, we're going to go to hydroxides next. And when we look at hydroxides, it turns out hydroxides are insoluble hydroxide salts. Those are insoluble, except group 1 and ammonium. Group 1 and ammonium are all soluble for the most part. Group 1 and ammonium, these are rules, by the way. Group 1 and ammonium, there's always exceptions. Group 1 and ammonium and calcium, strontium, and barium. So what this means is calcium hydroxide is soluble. Strontium hydroxide soluble, barium hydroxide soluble, sodium hydroxide, lithium hydroxide, cesium hydroxide, ammonium hydroxide, those are all soluble. Everything else is insoluble. So if we had, let's say, if I had magnesium hydroxide, insoluble, calcium soluble. If I had aluminum hydroxide, insoluble, lead-2 hydroxide, insoluble. So pick any. Chromium-3 hydroxide, insoluble. Yeah. We're going to go to sulfides. Sulfides are insoluble, except group 1 and ammonium. If I look at the cation first, I can eliminate that in group 2. And so that means magnesium sulfide soluble, but in addition to magnesium sulfide, calcium sulfide soluble, strontium sulfide soluble, barium sulfide soluble. And so that's what we got for this. But everything else is insoluble. So aluminum sulfide's insoluble, zinc sulfide's insoluble, cadmium sulfide's insoluble. G. Okay, the last series of anions that we're going to look at are phosphates, carbonates, and chromates. These are insoluble with very few exceptions. The only exceptions here are group 1 and ammonium. But otherwise, that's it. And so we can kind of get an idea of the states because magnesium solid, this is insoluble. Metals are insoluble, like iron doesn't dissolve, copper doesn't dissolve, silver doesn't dissolve, and water, gold doesn't dissolve. One way to get magnesium to dissolve is attack it by acid to oxidize it with sulfuric acid. Sulfuric acid is group 1, so we say that's soluble, so we put an aqueous there. And then this is going to go to magnesium sulfate. Well, sulfates are all soluble except for calcium, strontium, barium, silver, lead, mercury. And so this is a soluble sulfate, therefore it's aqueous. If there's water around, that salt will dissolve. Well, there's water around from the acid. You know, the acid is a mixture of H2SO4 and water, so water is present. And if water is present, this dissolves. Now the hydrogen, hydrogen is what we call nonpolar, like oil. So hydrogen likes oil, but it doesn't like water. And we'll talk about polarity later. It has to do with these electrical, how the electron cloud is distributed, or electrons are distributed in the molecule itself. And so solubility is going to give us an idea, does it dissolve? Aqueous, it means it dissolves. Therefore, aqueous species are soluble, aqueous species are soluble. Okay, and if it's not soluble, then it's just going to retain its state, whether it's a solid, liquid, or gas. Okay, the next thing we're going to look at is electrolyte properties. Okay, this is also in chapter 9. Electrolyte property says if it dissolves, does it dissociate into ions? Electrolytes are these solutions of ions, basically. And so let's look at what we call a strong electrolyte here. A strong electrolyte would be something like sodium chloride. Like sodium chloride is a strong electrolyte because sodium chloride, one, it dissolves. And so if I add water to salt, it dissolves to form NaCl, aqueous. And what happens is when the sodium chloride dissolves in water, the lattice gets broken apart into individual ions. And so this is the electrolyte. And so the first step is to look at its solubility. And the second step, we look at its electrolyte properties. So sodium likes to dissociate into the ions, sodium ions and chloride ions. And the sodium ions are going to be dissolved in water, aqueous, and the chloride ions will be dissolved in water, aqueous. And so we look at two things, the solubility in water and the electrolyte properties. And then we'll see, if we see something that's labeled NaClAq, this is the insight that we got. And so this is a beaker here, and we have a solution. And this is labeled NaClAq. What are we going to find inside this? What we're going to find inside this are sodium ions and chloride ions. We aren't going to find any molecules. And so we're going to find the dissolved ions in here. Dissolved ions. These dissolved ions form an electrolyte solution. Electrolytes actually conduct electricity. Do you know pure water does not conduct electricity? If I have pure water or distilled water, let's call it distilled or purified water. Distilled water is what we call an insulator. It doesn't really conduct electricity. You need salts dissolved in the water. So sodium chloride, this is an excellent conductor of electricity. Salt water. Salt water is an excellent electrolyte, an excellent conductor of electricity. It depends on how much salt. The more salt you have, the better it is. If you have trace amounts and it's almost like pure water, then it's not going to conduct very well. But you need a decent amount of salt in there, and then you can get good electrical conduction. This is why you'd never have water around electricity, because you can electrocute yourself. Salt water is a good conductor of electricity. And so we got to be careful. And so first off, let's try to recognize electrolytes. And then after that, we're going to see what implications that has for chemical reactions. Okay. This this is a precipitate here. This kind of orange is a precipitate, and that precipitate is an insoluble. Oops, what happened? Actually, I guess you can't see that, can you? Let me go back to it. All right, hopefully you can see this now. I'll post these PowerPoints, but there's not much explanation on here. Okay, this is a precipitate, abbreviated PPT. And the precipitates are insoluble solids. And so it doesn't want to dissolve in water here. And this one is a hydroxide. This is iron 3 hydroxide, FeOH3. Now the rule is hydroxides are all insoluble except for group 1, ammonium, and calcium, strontium, barium. Well, iron's not one of those exceptions, so this is a solid. And so insoluble solid gets the I, and it's a solid phase. This is what we call a gelatinous precipitate. You see, it's kind of like a gelatinous type texture to it. Even down here, it could be like gelatin. And so it's not very dense. You know, sometimes you get a very dense precipitate, it just sinks like a rock, you know, to the bottom. It precipitates. So this is like an orange gelatinous precipitate here. This is one way you can tell, you know, if you, let's see, if you have an electrolyte, is by having this. Basically, in order for this light bulb to light up, we have to have a closed circuit, you know, that is, we have to have electricity be able to flow through this. But it turns out it hits here and it has to jump over here, and it's not going to jump over here unless you touch them. If you touch these, then we close the circuit and then we get electricity. If we don't touch them, the circuit's open here. There's nothing connecting the wires. These are just two bare wires stuck out there. There are different ways to close the circuit. The way we're going to use to close the circuit is by using salt water. If we use salt water like this, now this isn't table salt, this is copper 2 chloride. Now copper 2 chloride is a solid lattice like this here. So what we're going to have is something like this. CuCl2. The first question we ask is CuCl2 soluble? And then we go to the solubility rules, and is it soluble in water? Chlorides, bromides, and iodides are all soluble except for silver, lead, and mercury. So this is not an exception, therefore it's soluble. So the first thing that happens is this dissolves in water to form aqueous copper 2 chloride. Now the next question we ask is this: does this dissociate into ions? And it turns out that copper 2 chloride is a strong electrolyte, and it completely breaks up into copper 2 ions, and in this case 2 chloride ions. So for every copper we get 2 chlorides. So coppers are tiny here, that's the copper 2, the chlorides are much bigger here. And so when we dissolve the copper 2 chloride, it breaks apart into copper ions. Now here's a copper ion that's surrounded by waters or encapsulated by waters. In other words, this is what we call a hydration sphere. Here's another copper 2 that's completely hydrated or completely surrounded by waters. This one too. Same thing happens with the chlorides. The chlorides are going to be hydrated with water or surrounded by waters. But what we see is that the ions break apart from one another. Now they're individual ions. That's what we call a strong electrolyte. Strong electrolytes break apart like this completely. Now, non-electrolytes do not break apart. And so that goes for something like ethanol. Ethanol is a different story here. When we have ethanol, which is CH3, CH2OH, Ethanol in pure form is liquid. So we could buy 100% ethanol, it's a liquid. The first thing is, does it dissolve in water? It does dissolve in water. That we're going to look at later when we look at the structure of these. But it turns out ethanol is an alcohol. Alcohols and water are alike, and so they like each other. This part of ethanol looks like water. This part of ethanol looks like water. You know, and so that's how they're alike. If you look at that and you look at this, they're very similar. And so ethanol dissolves in water. So that's CH3CH2OH aqueous. Now the next question we ask is an electrolyte. Electrolytes break apart into ions. And so if we think about what ions would ethanol break up into, would it break up into hydroxide ion? And it turns out no, because this is not a cation and an anion. This is what we call a covalent compound, which we'll talk about later, or molecular compound. So it doesn't break apart. And since it doesn't break apart, it stays together. And so no ions are formed. And so if I have ethanol and water and there are no salts in there, it doesn't conduct electricity. It doesn't close the circuit. Here, the salt, this is blue because copper 2s give it a blue color. But this salt water here, do you see how it lights up the bulb? This salt water closes the circuit. So now what happens is the ions can help conduct electricity. We need charged particles to conduct electricity. Over here, there are no charged particles. No charged particles, we can't conduct electricity here. And therefore the bulb doesn't light up. And so this is a non-electrolyte. It doesn't split apart. And then we have something in between. You know, in between is a weak electrolyte. Weak electrolytes partially split apart. And so something like acetic acid is a weak electrolyte. You know, one thing, acetic acid is group 1, and so it's soluble. And so acetic acid pure is a liquid. And does it dissolve in water? Yes, acetic acid molecules dissolve in water. So that forms HC2H3O2 aqueous. And then does it break apart? Yeah, a tiny bit breaks apart. A fraction of this breaks apart, but mostly it doesn't break apart. And when it breaks apart, it breaks up into the H+ ion and the acetate ion. Here. And so we get a small amount break apart. In fact, it's 99.9% intact molecules and 0.1% broken apart, less than 0.1% broken apart. And so that creates a small fraction of ions. That small fraction of ions can dimly light the bulb. So you can see the bulb is not as bright here because there are fewer ions conducting electricity. So weak electrolyte conducts electricity poorly because so few ions are present in solution. So few ions are present because most of the molecules don't break apart. And so it's a weak electrolyte. Now, how do we recognize strong electrolytes? Sorry I didn't put these slides up earlier. But strong electrolytes, what strong electrolytes are strong acids, strong bases, and soluble salts. These are strong electrolytes. Weak electrolytes consist of weak acids, like acetic acid is what we call a weak acid. Copper 2 chloride is what we call a soluble salt. So weak acids, weak bases, and some heavy metal salts, and some heavy metals. Heavy metals would be like lead, you know, mercury, heavy metal salts. That's it. And then non-electrolytes would be everything else. If it's not strong and it's not weak, then it must be non. So everything else would be like alcohols, that kind of stuff. Else here. All right, so what we're going to do, actually here, let me see this. Is let's take a look at recognizing. We want to try to recognize certain things. I guess we'll get practice doing that as well, but. Well, let's try to classify these ones here as weak, strong, or non. Now, in order to do classification, we need to know what strong acids are and what the strong bases are. And so let me tell you what the strong acids are. When we have acids, when we have acids, one way of recognizing an acid is acids begin with an H. And so this is an acid, this is an acid, this is an acid, acid. This is not an acid, this is an acid. And what we need to know are the 7 common strong acids. And then what we're going to do is we're going to assume all other acids are weak. And so let me tell you what the 7 common strong acids are. Can you guys see what I'm looking at right now? I don't know if you guys saw that, but this is what I'm looking at. And so what are the 7 common strong acids? Okay. The 7 common strong acids are going to be perchloric is 1, and then chloric is 2, and then hydroiodic, hydrobromic, hydrochloric. How many is that? 1, 2, 3, 4, 5. Then we're going to have nitric, and we're going to have sulfuric. 3, 4, 5, 6, 7. That's it. These are the 7 common strong acids. If it's not one of these, then we assume it's weak. The strong bases are more tricky. And so the strong bases I'm going to hold off, but some strong bases will be like sodium hydroxide, etc. We'll look at those later. And so can you look at these and classify it, you know? So what you're looking for are strong electrolytes, or strong acids, strong bases, soluble salts. And then you're looking for weak electrolytes, which are weak acids, which is basically all acids other than the 7 common strong ones, weak bases, and some heavy metal salts. And so try to classify these as strong, weak, or non here. So I'll give you a minute to think about those. I can't. All right, let's get back to this here. Okay, this is C12H22O11's table sugar. Table sugar, the first thing we ask is sugar soluble or not soluble? Tell me. So if I had sugar and water, would it form an aqueous solution? It's soluble, that's correct. And so this would be, if there's water, if water is present, for electrolytes, we need water. And so when water is present, this should be AQ. If there's no water present, then this should be solid. Okay, what did you get? Strong, weak, or non? So it's a process of elimination. Is table sugar a strong acid? No. Is table sugar a strong base? No. Is table sugar a soluble salt? Soluble salt, salts are ionic compounds. This is molecular. No. Is table sugar a weak acid? No. Is a weak base? No. Is it a heavy metal salt? No. Therefore, it's got to be a non-electrolyte. Non-electrolyte means they don't break apart. It's non-electrolyte. Now, what else they're saying or asking is, if it doesn't break apart, what's a major species found in water? The major species are just the molecules themselves dissolved in water. So the sugar molecules themselves dissolved in water. What's the minor species? No minor species here, none. Okay, let's go on to the next one. HNO2, what's a name for HNO2? HNO2. Close. Nitric acid is HNO3. Nitrous acid, that's correct, nitrous acid. And so just once I answer the rest of the question, I have to. All right, sorry about that. Okay, let's continue on here. So nitrous acid is a weak acid. Weak acids are weak electrolytes. How do I know it's a weak acid? How I know it's a weak acid is it's not one of the 7 strong ones. You know, the 7 strong ones I had posted on the chat. And so this is a weak electrolyte here. What weak electrolytes do is they partially break apart. And so the major species is the molecule HNO2 together. The minor species would be a small fraction of these HNO2 molecules break apart into the ions. What are the ions? H plus and NO2 minus. H plus and NO2 minus. And so we expect in this solution should consist mostly of HNO2 molecules and a tiny bit. So this will light the bulb up dimly because there's small population of ions present here. Okay. HF, what's that? The name. H, well, it begins with an H, so it's an acid. And so what's the name of that acid? Yeah, that's correct. Hydrofluoric acid, Francis. Is it soluble or insoluble? It's soluble. So this would be HF aqueous. Is it a weak acid or a strong acid? Yeah, it's tricky. It's not strong. HF turns out to be weak. It's really weird. HCl is strong, HBr is strong, HI is strong, HF is weak. And so it doesn't go with the rest of the group. You know, you expect HF to be strong, and it should be strong. And the reasons why it's weak, which we'll talk about when we get to the acids chapter. But it turns out HF is the odd one in the family. All the other ones in the family are strong, except for HF. Now, HF is a weak acid, but it's very reactive chemically. You know, it has a different type of chemistry. So HF isn't like a great acid, but it's very reactive in terms of metathesis. And so HF can be very dangerous, even though it's a weak acid, because of its metathesis reactivity. We'll talk about that more later. And so HF here is weak acid. Weak acids are weak electrolytes. Weak electrolytes don't really want to split apart, and so they stay together. And so we get HF aqueous molecules, and very few of these molecules break up into the ions. And when they do break up, they'll break up into H plus and F minus. So these are minor species. These ions conduct electricity. Since mostly we have neutral molecules, it doesn't conduct electricity all that great. Sugar water doesn't conduct electricity at all. You know, the sugar waters be a non-conductor as long as the water is pure, you know. Okay, LiF is lithium fluoride. And so is lithium fluoride soluble or insoluble? Okay, we have to look at the solubility rules. It's a ionic compound, and so we look first for the cation. If the cation is group 1 or ammonium, then it's soluble. Well, lithium is in group 1. It's the alkali metals are group 1. So this is soluble. If it's soluble, does it break apart? Well, it's a soluble salt. Soluble salts are strong electrolytes. So if we have a soluble salt, lithium fluoride, it's a strong electrolyte. Now, strong electrolytes want to break apart completely. You know, strong electrolytes break apart 100% is what we say, or close to 100%. And so they're going to completely break up into ions. And so the major species will be lithium ions and fluoride ions. And since it's strong, we don't expect any intact formula units. So there should be none. And so it's all broken up into ions. There are no molecules or formula units left. Okay, let's go on to number 7 here. HClO4. What's the name of that first? HClO4. Yeah, good. Perchloric acid. And is perchloric acid soluble or insoluble? It's soluble, you know, group 1. Is it a strong acid or weak acid? Well, Kazra has it. It's strong acid. Strong acids are strong electrolytes. Strong electrolytes want to break up completely. So what does it break up into? It's going to break up into H plus and ClO4 minus. H plus, the hydrogen ion, and ClO4 minus. ClO4 minus is perchlorate. And since it's strong, it completely breaks up. So there's nothing left over. In this case, strong electrolytes, we assume 100%. So we could say none or trace amounts, very small amounts of HClO4 left over. Okay, now this one you probably don't know, but even though you don't know the name for this, you should, even though you may not know the name for this, you should be able to tell me if it's weak or strong. You should be able to tell me it's an acid because it begins with an H. And so it is an acid, but is it a weak or strong acid? Let me know. It's a weak acid, right? It's a weak acid because it's not one of the 7. This acid is called formic acid. Formic acid. And it's a weak acid, therefore it's a weak electrolyte. And weak electrolytes don't like to break up. And so the major species are going to just be the molecules of formic acid. The minor species will be, well, a few of these molecules will break up into H plus, and the CHO2 minus is called the formate ion. So H plus and CHO2 minus, which is formate ion. Okay, let's move on here to this one. This one you should know. It's this one called ammonium nitrate. Good. Now, ammonium nitrate, is it soluble or insoluble in water? It's soluble. All ammonium salts are soluble. In fact, all nitrate salts are soluble. So this is very soluble in water. So soluble salts are strong electrolytes. Soluble salts are strong electrolytes. And what do strong electrolytes want to do? They want to break up into their ions. What are the ions? We have ammonium ions and nitrate ions. This should be none here. None. It's all broken up. Okay, number 10, you should recognize this acid. This is a very common acid, also known as vinegar. And so vinegar consists of acetic acid, that's correct. And is acetic acid soluble? Yeah, it's a group 1. We're going to assume all acids are soluble. It's not, always correct, but that's what we're going to assume. Is it a strong acid or weak acid? It's a weak acid. And weak acids are weak electrolytes. Weak electrolytes don't like to break up so much. And so most of the vinegar is going to have acetic acid molecules dissolved, not broken up. And a small fraction of these molecules are going to break up into ions here. Hydrogen ions and acetate ions, just a small fraction. So vinegar conducts electricity weakly compared to a strong acid, like this one. HCl, what's it called? HCl is about the most common acid in the laboratory. Hydrochloric acid. Hydrochloric acid is one of the 7 common strong acids, and that's a strong electrolyte. Strong electrolytes love breaking apart completely, and so this should break up into the ions. What are the ions? H plus and chloride. And this should have nothing, just a trace amount of intact molecules, maybe. Just a trace amount of intact molecules, but nothing significant. C6H12O6, you probably don't know this one. This one is sucrose, table sugar. This one is glucose, another kind of sugar. Sucrose is made up of glucose plus fructose. And so this is just the glucose. And so table sugar is what we call a disaccharide. And glucose is what we call monosaccharide. Now, is glucose soluble? Well, are sugars soluble in water or insoluble? This just comes from experience. Once we know structure, then we'll see there's certain structural cues that tell us sugar and water like each other because they're similar in certain ways. One of those is alcohol. Sugars have alcohol groups on them, although it's not considered an alcohol because there's other stuff in there as well. And so sugars are soluble. But the situation is, are they strong, weak, or non-electrolytes? So we ask ourselves, is glucose a strong acid? No. Is it a strong base? No. Is it a soluble salt? No. It's a soluble molecular compound, but it's not a soluble salt, which is an ionic compound. Is it a weak acid? No. Is it a weak base? No. Is it a heavy metal salt? No. Therefore, it's a non-electrolyte. And non-electrolytes do not break apart. And this should be none, because none of these should be broken apart into ions. They are not made of ions, made up of ions. And so that's it. And so there's a little bit of practice. Now, how do we deal with this in the context of what we're just doing? In the context of what we're just doing with the reactions, we want to better understand some of these reactions. Let's see, where was I? Okay, so I'm talking about electrolyte properties. Now I'm going to go back to this one. Magnesium plus H2SO4 yields magnesium sulfate plus H2 gas. And so what we're going to do is we're going to try to analyze this reaction in more depth. And so we're going back to the reaction magnesium solid plus H2SO4 aqueous. Acids are soluble, yields magnesium sulfate, MgSO4, plus H2 gas. Now, sulfates are all soluble again, except for silver, lead, mercury, calcium, strontium, barium. So this is an exception. So this is soluble, like that. And so basically, this is the way I can visualize it. Over here, I'm going to take some magnesium solid. So this is going to be magnesium solid. And I'm going to mix it with some H2SO4 solution. This is going to be H2SO4 solution. And then in the end, I'm going to have some hydrogen gas. This is going to effervesce. And so I'm going to have bubbles of H2 gas form. Those are going to escape from the water. And I'm going to have magnesium sulfate in this beaker here. And this magnesium sulfate is going to be aqueous. So this is what we call the complete equation here. Complete equation, which I'm going to label CE. Okay, then we're going to have something called the ionic equation. The ionic equation is going to give us a more detailed picture of what's going on. And so when I look at the ionic equation, what we're going to do is we're going to dissociate strong electrolytes. So magnesium solid metal. Magnesium metal is not a strong acid, it's not a strong base, it's not a soluble salt, it's insoluble. It's not a weak acid, not a weak base. We just leave it alone. And so we dissociate strong electrolytes, leave all else alone. Leave all else alone. And so we're going to leave magnesium alone. But then we get to H2SO4. And H2SO4 is a strong acid. Strong acids are strong electrolytes, so we have to dissociate that. But the H2SO4 dissociates funny. H2SO4 is called diprotic acid. And when one of the H's breaks off, then we're left with HSO4 minus. Now, does the second H break off easily? Well, is HSO4 minus a strong acid? If HSO4 minus is a strong acid, then the second H plus breaks off. No, it turns out that this is a weak acid. And so what happened is the H2SO4 is a strong acid. The first H plus breaks off, but the second H plus has difficulty breaking off because this is a weak acid. It's not a strong acid. And so we stop at one hydrogen breaking off. It's going to take more work to break off the second one. Okay, this is going to go to magnesium sulfate. Now, magnesium sulfate is a strong electrolyte, and because it's a soluble salt. So strong electrolytes like to break up. So this is going to break up into magnesium ions and sulfate ions. That. And then hydrogen gas is a non-electrolyte, so hydrogen gas stays intact. And so this is called the ionic equation. So in the ionic equation, this is what we have in the beaker. And so here we're going to have some solid magnesium, and inside the solution we're going to have H plus, acid, and HSO4 minus acid. H plus is a stronger acid here, and so we're going to have these species in here. And what's going to attack the magnesium first is the stronger. What's stronger here is this H plus. This H plus, oops, will react first, and then this H will react. Okay, after the reaction's over with, what we're going to be left with is this. We're going to be left with magnesium ions in solution. We should eat up all the magnesium metal. Sulfate ions in solution, and then hydrogen gas is going to bubble out. And so this hydrogen gas bubbles out the solution here. And so this kind of gives us a more descriptive picture of what's going on, what's reacting here in this. And so this is the ionic equation. And then we have something called the net ionic equation. The net ionic equation, we have to cancel spectators. And so eliminate spectator. Spectators are like, X in single replacement, nothing happened. And so magnesium, something happened. This is not a spectator because we go from magnesium 0 to magnesium 2+. And so we go from metal to an ion. And so these aren't the same thing, even though it's Mg. Mg0 and Mg2+ are totally different. H plus and H2 are totally different too. This is acid, this is hydrogen gas. H plus is not flammable, H2 is highly flammable. And then we have HSO4 minus going, and then we have SO4 2 minus. So these are different in terms of acid-base properties, which we'll talk about later. And so there are no spectators here. There's nothing that didn't change going from one side to the other. And so this is what we call the IE and the NIE together here. And so we're going to be doing this for our reactions. We're going to be analyzing them in terms of solubility, in terms of electrolyte properties, that kind of stuff, and then looking at the ionic and net ionic, which can give us a deeper insight into what's going on with these particular reactions. So that was number 20. And let's take a look at the other one. Chlorine gas is bubbled through an aqueous solution of potassium iodide. Now, this one is a bit tricky. Come on. Okay, I can't write on this anymore. For some reason.
Professor, you're on mute. Professor?
You're on mute.
I get on mute. Sorry. Hey, did you guys hear all the discussion I was talking about earlier with magnesium sulfate? Or have I been on mute all this time? Okay, the magnesium bit you heard. Did you hear the whole discussion about electrolytes? Yeah. Strong electrolytes, weak electrolytes, non-electrolytes. Did that work? Okay, that worked. All right, well, I got to figure out what's going on with my speaker. You know what I'm going to do? Since I got to repeat, I will repeat what I was saying earlier. I'm going to, let's close out for today. And then we'll continue this tomorrow. Okay. Were there any questions before we leave today? I'll go back and talk about what I was talking about earlier. I don't know how I muted myself, but from there. Okay. All right, then. All right, thanks for your patience, and we'll see you guys tomorrow. For the exam, do we need to show you how we balance the charges? For the formulas, no, you don't have to show me. I showed you how I balance the charges mentally. You know, after a while, I'll just do it mentally in my head and then just write the formula. When you guys write the formulas, make sure you don't do this. You know, let's say I'm asking for the formula for aluminum iodide. I don't want to see this. I don't want to see +3 and then -1. You know, there should be no charges here. And so if you write that to help yourself, make sure you erase it or cross it out, because the formula for aluminum iodide is just this. There should be no charges above there. And so a lot of people write the charges there to help them, you know, get the right ratios. But I don't want to see the charges there, because if somebody asks for aluminum iodide, it's just Al(I3), no charges. Okay. If I ask you for an ion, yeah. If I ask you what the charge on aluminum is, you better write it on there, Al3+. Or if I asked you for iodide, you better write iodide, I-. Or if I asked you for carbonate, you know, it's CO3 2-. You have to write the charges there. But you know, that's naming carbonate. Now, if I asked you for magnesium carbonate, there better not be any charges there. If I ask you for magnesium carbonate, I don't want to see any charges. And so if you use the charges to help you, so for example, magnesium is 2+ and carbonate is 2-, this is not the formula for magnesium carbonate. The formula for magnesium carbonate is MgCO3, no charges there. But it depends on what I ask you. And so if I'm asking you for carbonate, yeah, if I ask you for the formula for an ion, always write the charge of the ion. If I ask you for the charge of an ion, if I ask you for the compound, you know, if I ask you for the formula for an ion, I don't know what ions, I had lots of ions on there. You should be writing lots of charges on there. And so I could ask you for antinomide, you know, antinomide. Well, antinomide should be Sp3 minus, you know, I'm not going to ask you that, but if I ask you what the formula for antinomide is, that's what it should be, you know. And so so whenever you're doing nomenclature and you need to write the formula for an ion, make sure you write the charge. For compounds, compounds are always neutral. Ions are always charged. You can tell if it's an ion. So for example, if I say chloride, it's got to be an ion. And therefore its formula is Cl minus. Okay, were there any other questions? No? Kazra, that's good. Okay, if anything else comes up, let me know. Anybody else? All right. So I guess I'll see you guys tomorrow. Just keep working on the exam. The upload link is on Canvas, but it's not due until Monday morning, so you don't have to turn it in until then. Okay, great. All right, see you guys tomorrow. I'm going to end the room now. Bye.